Hi, everybody. Welcome to the April 2025 SJAA imaging meeting. And tonight we have Steve Mandel talking to us about the amateur deep field project. Please take it away, Steve.
Okay. Well, I think I'm going to share the screen here first. So get the presentation up. You see that okay?
It's all good.
Okay, good. Well, first of all, thank you, Hi, and thanks to everybody who's attending this evening. I'm really flattered to be here and looking forward to talking to you about the Amateur Deep Field Project and how I got there. So I'm going to start in the present and work towards the past. So I'm going to tell you about what this project is and what happened with the project, and then go into a little bit of my journey to bring me to do something like this. And the background image right here actually is an image that was taken by 10 telescopes in the southern hemisphere who participated in this project. And it is, and we're just talking about stacking before we started the recording here. And this is a stacking of, you ready for this, from 10 different telescopes, a total of, I think, about 295 hours of images stacked up so we could get very, very deep. And I'll tell you about what some of these things are that we found in the image here. Slide. So here is the famous image, the Hubble Deep Field Image taken in 1995. And then I think it was released to the public the following year. And the guy who ordered this image to be taken, his name is Robert Williams. And it goes by Bob. And so I work as a research associate at the UC Santa Cruz Department of Astronomy and Astrophysics. And research associate means I get to do what I want, but I don't get any money or any benefit. And I get to use the resources, not the big telescopes, but what I get access to were journals and research. And I've gotten to know a lot of the astronomers. And one of the astronomers is Bob Williams, the guy who was the director of the Space Telescope Science Institute starting in 1993, which they put together when Hubble went up. And the first thing they had to do was fix Hubble. So he was there and helped the Hubble get fixed. So when it got fixed, they could start taking pictures. And as director of that institute, Bob was given essentially 10 days a year in which he could use the telescope for any project that he wanted. And so he had an idea, and he said to his staff, why don't we point it at nothing? Why don't we point it at a dark patch of sky and see what happens? And this was very controversial. And when word got out that they were planning on taking 10 days of the Hubble, which cost billions of dollars, and was broken, and the space shuttle went up and put in the fix for the lens and went through all this stuff, that he was going to point the telescope 10 days of precious time at nothing. And so and there was a lot of controversy, but he said, no, this is what I'm going to do. This is my time. He did it. And what you see on the screen here is what came back. And it turns out that this is one of the most iconic science images, if not just, photographs ever taken, because it completely changed our view of the universe and what is out there. And this dark patch of sky was filled with galaxies. I don't think I see one star. Maybe there's a couple other stars, but everything you see in there, down to the faintest little dot, those are distant galaxies. And when people saw this, they were absolutely astounded. Astronomers were astounded. The public was astounded. And everyone had to rethink their view of the universe. And it made everyone feel much smaller than we already felt because there were so many more galaxies out there. And you can see the great variety of the galaxies in this photo. So it was quite amazing. And then it was so successful, the Hubble did the Hubble Extra Deep Field. I mean, they had other projects where they replicated this, and everywhere they looked at a dark patch, the dark patch was filled with millions of galaxies. So it was quite extraordinary, and you know, a lot was written about it. So that was back in the 90s. Bob then left. He did research. He is now, I think he's 84, 85 years old, but you wouldn't know it when you meet the guy. You know, he's quite amazing. He's still doing research, and he's an adjunct faculty member at UC Santa Cruz. He and his wife were actually in the process of moving to California. They've lived on the East Coast for many, many years. So I was asked about, a decade ago, to become a mentor for astronomy grad students and postdocs, and to go in and bring some of the skills that I had from my consulting work with technology, which was essentially training people in technology how to structure and deliver messages. And they wanted me to train astronomy grad students on how to do that. And so I worked for almost all the high-tech firms in the Valley. I worked, you know, internationally, you know, globally. I ended up hiring people. We had about 35 people spread around the globe, did a ton of this training. And I started working with these grad students because I understood the science, because I've been an amateur astronomer since I was probably 10 years old, and wanted to be a professional astronomer, but ended up doing different things in school. But I've always studied astronomy on the side. So I got to know Bob because he was part of this program also, and he's a wonderful guy. And a little over a year ago, I was chatting with him, and I said, "What year did you take the Hubble Deep Field?" And he said, "Well, that was back in 1995. I said, "Oh yeah." I said, "Wait a second. That means 2025 is the 30th anniversary of that image." And he said, "Yeah, that's right." So every year, my wife and I sponsor a lecture for the public that's held at a big movie theater in Santa Cruz, and we invite an astronomer to come and give a talk. And I said, "Well, why don't you do the lecture this coming year?" And he said, "Okay, I'll do that." And then I had this brainstorm of an idea, and I called him up and I said, "I got an idea. I want to know what you think about it. I'd like to organize a bunch of my astronomer friends. Some have telescopes in the northern hemisphere, some have telescopes in the southern hemisphere. And I want to point at a dark patch of the sky and do the amateur deep field and see what we get. Because we've got, you know, some pretty good sized telescopes, and the technology has really advanced. We're using CMOS sensors, you know, and as opposed to film, although this was a digital image, of course. So he said, that would be fun. Do it." So that's how the whole thing got started. It was, you know, inspired by what Bob did 30 years ago, you know, having the courage and the foresight to, you know, tell people, I'm gonna photograph nothing and see what happens, because maybe there is something there. So I organized this big project, and you know, Bob became our advisor. Connie Rakosi is an astronomer up at UC Santa Cruz, and then there were some guys who go by the Deep Space Collective. They organize big projects like this where a bunch of people are kicking in, and one of those is Carl Bjork, who I'll show his picture in a second. But this guy, Tim Schaefer, is in Belgium. I've never met him in person. I've never met Carl. Carl's in Switzerland. Steve Boddy is in Melbourne, Australia. And I got to tell you, Tim Schaefer is 20 years old. and he's brilliant. He's a university student. And he's an old soul, this guy. He's smart and mature. He's not like any 20-year-old I've ever known. And so they organized groups of amateur astronomers to take pictures of things and put the images together. Someone told me about them, and I told them about my idea, and they said, well, we'll help out. We know how to organize this. And I said, okay, that'd be great. And then my son is a software engineer, and he used to be at Google also. So both my boys were at Google for a while. And so I needed some help with survey data that I'll tell you about in a second, integrating it into a planetarium program. And I used the Sky. That's the program I'm used to. So I had to figure out how to get professional survey data into the Sky so I could identify some of the things that you'll see in the photo. And then I enlisted a couple of partners, Sierra Remote Observatories, which is a telescope hosting facility up in the Sierra Nevada, and then OBSTEC, which is another telescope hosting facility that's in Chile. And my partner and I, Bob Farah, we have a 17-inch CDK up at Sierra Remote and the same telescope at OBSTEC in Chile. And so I know other amateur astronomers who have telescopes, because each of these hosting places has this blew my mind when someone told me this, they have over 100 telescopes in each location. And so there's a lot of people there, and I knew some of the folks who had the telescope. So I reached out to them, and the ones who responded, you see below that. So the Northern Image Partners, there's the list of people who helped out. And down in Chile, the Southern Image Partners, people who had telescopes there who agreed to help out with this. Oh, and Astroval, they have a big observatory in Switzerland that Carl got to use. And LTEC is actually Carl donated some of his company time to doing some work. And then we did put together a little website, which you've already received in the invitation that Hai sent out, the Amateur Deep Field website there. So I had all in all, there was over 30 people involved in this because there were a bunch of stuff to do. And imagine if you get 300 hours of images from 10 different telescopes, putting those images together because you have different focal length telescopes. It was quite difficult, quite complicated, but that's, Tim and Carl and Steve all worked on the images. So it was really a fantastic effort, and an effort by many people to make all of this work. And by the way, if you do have any questions, just come off mute, interrupt me. I don't mind. I'm happy to answer any questions at any time. Okay. All right. So here's Carl, and he got to use this 24-inch telescope. And this is somewhere in the Swiss Alps. So he was quite happy because they let him use the scope for the project. And here are some of the telescopes that were used. So this is my friend Kevin Moorfield, that's in Chile. Whoops. Let's see here. There we go. And this is a 17-inch, and this is the plane wave Delta Rho that he had. This is a 20-inch that I believe is, where's this one? This one is here in California. This one's in someone's backyard, Kentwood in Utah. And this one, I'm not sure where this one is, but that might be Chile there. And this is Bob Farah, who's my telescope partner. And this is our 17-inch CDK. We were there installing this. And so these are the kinds of telescopes that were used for this project. So here's Bob starting out the lecture, talking about, the Hubble, 30 years later. And the lecture is available. It's on YouTube. And if you take an hour and watch it, I give a short presentation. It's about 10 minutes long on the Amateur Deep Field project. You can watch that, but you're seeing this, so you can skip it if you want. And go to Bob's and listen to his presentation. It's really excellent. It's really interesting. And I won't tell you what he said at the end, but it was great. His conclusion about all of this. So he's a wonderful speaker and just a brilliant guy. And I hope my mind works as well when I'm 85 years old. So here is a screenshot from the sky. And what I had to do, as I said, and my son helped me, is figure out how to get these green dots in here. These green dots represent survey data. And there were a couple of major surveys done, spectral surveys with ground-based telescopes. One of them is the Sloan Digital Sky Survey. And this one comes from GAMMA, which is the Galaxy and Materials something. It's kind of a funny title. But both of these surveys with large ground-based telescopes got spectra. And once you get the spectra, you can measure the redshift. And the redshift is expressed right here. So astronomers use the letter Z as an expression, and you see a numerical value. That numerical value can then be changed into light years. So we know the distance of the object. And so the light travel time is 4.5 billion years. And that's for this thing that's circled right here. So I could, my son was just brilliant in setting it up. I can't tell you how he did it, but he got this data into the sky. So I could click on one of these green dots and it would read out the survey data for me. So I could tell you how far away something was. The trick was then on a photograph identifying this stuff. But this is how I started out. And I knew there were a few things in the field here, but I picked areas of the sky, one in the northern hemisphere and one in the southern hemisphere, that if you looked at with your naked eye, it would be pitch black. Even if you were in the Andes, in Chile, at an observatory site, you would see no stars there. I think we can see down to 7.5 magnitude. And some of the stars that were in these photos I'll show you were 12th magnitude. So they were, for the unaided eye, they were dark patches of sky. And I wanted to see what we would pick up if we did a couple hundred hours of exposure time. Hey, any questions so far?
Yeah, Steve, can you say what the field of view is? Oh, and also while you're at it, for the original, what was that field of view, and what is yours?
Okay. Well, they're pretty much the same, and I've had to go back. I'm sorry, I don't have that number right in front of me, and I can't remember what our exact field of view is. Oh wait. Oh yeah. Okay. So for each of the images that I'm going to show you, we were able to, in the images, do something like, well, it's a little smaller than the full moon. So that's the patch we were looking at, the dark area.
Okay, roughly half a degree.
Yeah, something like that. All right. You may have seen a diagram like this before, but this is, showing, you go back here, this is, the beginning of the universe, and this is approximately, as it says, 13.7 billion light years back. 13.8 is the number usually thrown around, and that's probably off at maybe 14 billion. But that's when the Big Bang occurred, and so each of these little vertical striations is a billion light years, and I'm going to show you how far back we got with some of this. And so when we started getting this in, and I started looking at the actual light years and the things that we picked up, it changed my own view of the universe. And if you're in astronomy and you like astronomy, as all of us are, and you think about this stuff, we're all kind of blown away about how small we are. The more I did this project, the smaller I got. And but in a good way, because I felt less significant, but I felt more a part of everything also. And I'll show you the pictures here. It just kind of blew me away. So So this was, 291 hours. And here is the southern image that we got. And you can see some of these galaxies are defined, and you see the stars. So the stars are the Milky Way, right? And we get, diffraction spikes from the telescope. And there's some other less bright stars. And my estimate is that about 1% of the objects in this photo are in our own Milky Way galaxy. So that are some of the stars. Everything else are distant galaxies. And I'm just going to randomly point. You see those three little dots right there that I'm circling? Those are distant galaxies, and as are all these little dots. And I was astounded, just like the Hubble picture. Now the Hubble, because it's, like 250 miles above the Earth and doesn't have the atmosphere, it's a big telescope, is able to resolve things. And here we started to resolve some of these distant galaxies. You see some of these here. But this just kind of blew me away when I started thinking about the number of galaxies, and each of those galaxies, if it's the size of the Milky Way, it has somewhere between 200 and 400 billion stars in each galaxy. And so my vision of the universe changed in this project. It became so much bigger to me, and maybe more beautiful also, just in its vastness. Okay, so here is the data, the survey data applied. So this is all from the galaxy and material analysis or something like that, the gamma survey. And I put the Z factor in. So when I show this to astronomers, they know what the redshift factor is. And then I translated the redshift factor. There's actually an online calculator to tell us how distant these are in light years. And here's our record holder right here, this guy, 11.3 billion light years. So this is going back to what, the universe was only 10% of its age. And this little thing shows up, and we picked it up on our telescope. Now, the light left there, of course, 11.3 billion years ago, and got to our telescope, and we picked it up. But the universe has expanded. So that object now is probably somewhere between 30 and 40 billion light years distant, just because of the expansion of the universe. But the light that we got left there that long ago, and we know that because we have an accurate redshift from these ground-based surveys. And you can see, the various distances here as you glance around. This one's a little closer, so we can resolve it. This little spirally thing here, only 1.4 billion light years, so on and so forth. And this little edge-on spiral, 1.1. So this was really quite amazing to look at this and realize all this other stuff. I wish I could get data on every single object in here just to know what it is and where it is. And you really have to think about this two-dimensional photo in 3 dimensions, because we have, the bright stars here, and here's this nice, look at this nice little double star in the Milky Way that's right in front of our faces. And then we have intermediate distance stuff, this galaxy and this one. And then we have stuff that's way in the distance, there. And undoubtedly there's more of those that are way in the distance. So this is really looking far back in time, far back into the universe, towards the beginning is what we're seeing in this photo, done with, 10 amateur telescopes in the southern hemisphere. Okay. Oops. So here. All right. This is the northern image now. And you can see, same story. We've got stars here. right, that are local. And unfortunately, this got cut off. This turned out to be I don't know if you've ever heard of the Hickson galaxy, but they're galaxy group. So this is a Hickson galaxy group that's up. And one guy actually went back and photographed this. He hasn't released the photo yet. It's a nice little galaxy. But all of these in the northern hemisphere just once again blew my mind. This is, 7 billion light years the light was traveling. There's 5. If this is closer in, so we can resolve it. This is closer in. There's probably 2 galaxies colliding here because you can see a star stream coming off this thing that's 842 million light years distant. And this is all from the SDSS, which is the Sloan Digital Sky Survey, where this data comes from. So this was the project to see what we could do, and it was inspired by the Hubble Deep Field. What could amateurs do? And we didn't equal the Hubble Deep Field simply because we don't have the resolving power. But I think we got pretty close in terms of, because we put so much time into each photo. And this one, I believe, was 295 hours of exposure time that we picked up all these these are all galaxies out here, all the tiny little pinpoints. So once again, we had really the joy of seeing our collective work look down that tube into the history of the galaxy. This is really an incredible time machine, when you think about it. So let me pause here for questions about this. And this was essentially the project. It lasted many months. It took 6 months because we had to wait for the object, the field to be well positioned. And there were other people who, the telescope broke down, or they got diverted to another project and who didn't participate. But the ones who stayed with it, this is their contribution, and this is how it all turned out.
I have a question here.
Yes, please.
Can you hear me?
And
Okay, good. So in a picture like this, how do you determine what is a galaxy and what's a star?
Okay, so the stars are bright because we expose so many hours, and those are the things that
Okay.
diffract, right? And there are some smaller ones as you keep looking, and there's maybe a couple more that don't have spikes, but just a very few. So we've got.
So that's what I was wondering about. I can see the brighter ones have spikes and therefore they are stars. But what about like a very, very dim star that's still in our galaxy that won't have a spike? How do you know that is a star?
Because there's probably a few of those in here, but because in this field, and when I looked on the star map, I could see what stars were there. So let me go back. Let's see what's the best way for me to do this. Use this key. So if you look here, you can see, there's some galaxies, and I don't have the stars turned on here, but there's only a few stars in this field. The red things,
Okay.
those are those galaxies. These are galaxies, and there would be a few stars sprinkled throughout this. And most of the galaxies in the photo, if we go back here, don't even show up on that survey because no one's photographed them before. So a lot of the stuff you're seeing in these photos, this may be the first time it's ever seen in a photo. We don't know. Unless it was picked to be surveyed, which were the green dots. But there's many more things here than green dots, and those are not stars. We know that those are galaxies because we're looking in an area where there's not a lot of stars. And just because we have so much exposure time, the stars tend to show themselves.
Right. Okay, a second question. Now, with all these many telescopes, did you have some kind of ground rules as to how, what they're supposed to do, how they're supposed to expose, how did you set the ground rules so you could later on merge them?
So that's where the help of the Deep Space Collective guys came in, Tim and Carl and Steve, because they had experience with this. So we had a very, I want to say strict guidelines, but we issued guidelines for, what amount of processing they could apply, which was not much, dark subtraction rules, flats. We had a bunch of criteria that for their photos to be accepted, for the data to be accepted, they had to follow that criteria. So we laid that out, and it worked pretty well. We even had there's rotators on the telescope, so we had everyone set it at 0 rotation. So we specified, what the rotation of the field was, a whole bunch of parameters. But everyone knew what those were, and they're pretty standard parameters, and people stuck to them. And we could tell if photos did not follow those parameters. And there was one set we got, unfortunately, where the person didn't follow it, and we could not use that data.
Let me add that in December we had a talk by Mark Scrivener, and Mark actually, as part of the talk, relayed information that the 3 collaborators of Steve's, used just to answer your very question, like the ground rules for exposure time and type of telescope and field of view and all those things. So if you look at our December talk, you'll see that on YouTube, and I'll put a link to that in case you guys don't know how to get to that. I'll put a link to the list of talks in the chat.
Okay. Any other questions before
Thank
I
you.
go on? So we have the website up. Sky and Telescope magazine is writing an article about the project, but that's a minor part, as it should be. It's mostly about the 30th anniversary of the Hubble Deep Field. So I put them in touch with Bob. So they've interviewed Bob, and they are putting this article together. They have a long lead time. So the article on this project and on the Hubble Deep Field 30th anniversary will be out in the December issue of Sky and Telescope. Any other questions about it? So I would just say, doing long exposures really paid off. And so for those of you with telescopes, you're probably picking up stuff in photos that, it's worth looking at. You don't just get stars. If you especially get into the springtime where, we're looking this way out of the plane of the galaxy. In the summer, we're looking, into it. So we see all the dust and the gas in the center of the galaxy. But in the springtime, we look straight out of the galaxy. So we can then visualize and see in our photos, a lot of very distant objects. And so it's really fun to try to identify what you have in the photos, or look at other people's photos and just contemplate stuff like this, these faint little dots and what you're looking at, because it could very well be, there's some guys in the some distant galaxy on a Zoom call, with their telescopes. I mean, it's fun to think about in my mind.
Yeah. So here's a question. Yeah, can you hear me? Yeah.
Yes, I can.
Yeah. So do you plan to basically update some of these surveys? Means if you discover new galaxies which are not currently in the survey, maybe if you have enough exposure, you can discover new galaxies, new structures over there. Because what we do with Mark, thanks, hey, mentioned, we actually integrate, we try to integrate as much as possible signal, so eventually we can get some sort of discovery of new structure. like a new nebula or new going in the sky. In this case, in your case, could be if you have enough exposures, you can discover new galaxies which are not in the survey or new objects that are not there. Have you tried that?
Yeah, I'm sorry, it broke up. If someone else could hear that, can you repeat?
Yeah.
I didn't fully understand what you said.
Okay.
My apologies.
It was.
I couldn't totally follow Nick's comment, but I think the gist of it, and correct me if I'm wrong, Nick, was to take your discoveries and add them to existing surveys. Does that make sense?
Yeah. So what I mean is that what we do usually, what we try to do with this joint project is if we not only to image something, but eventually to this, if you see something unknown, right, a new nebula, right? So I was curious if we, let's say, have enough exposures of all these images, that could lead to new discovery, let's say, to new galaxies that are not into the catalogs, right? That's what I meant.
Right. So, in terms of nebula, they're pretty close in. They're in our galaxy. So those are quite discoverable. On the other hand, the vast majority of galaxies you see in this picture and the other picture are not cataloged anywhere. There's no, I could pick some random little thing here and it's probably not cataloged, these. But it's a visual image is what we have here. And the only way that they catalog these items to get some data is by spectrographic study. So doing visual light, gives us a picture like this, but it doesn't tell us too much about the objects. Whereas when you get the spectra, that tells you a lot more, its distance, its composition. We can understand some of the chemistry coming from the galaxy. Or if you do radio study, you can get data from radio light or radio waves. So you could say with these photos, we discovered thousands of galaxies, but anyone can point their telescope anywhere, do a deep photo, and you're going to get galaxies that have not been surveyed, are not known, are not named, because they're everywhere. They're pervasive. So it's not of too much value unless you can gather additional data, and that's why these studies all use spectra, because that's the only way to really kind of understand and measure where it is. Does that make sense?
Yes, absolutely. Yeah. Thanks.
Okay. Thanks for the question. Okay. Well, now I'm gonna shift gears a little bit here and talk about how I came to do all this. So give me 1 second. I have to jump up here at my office. And this used to be, well, it's still my backyard, but I don't have these buildings anymore. These were in the 1990s, and that was my dog Goldie. His nickname was Goldie the Astro Dog because he would hang out with me at the observatories. They're a very sweet, wonderful dog. I've had him 10 years. I now have another dog, Lily. And I called it Hidden Valley Observatory because we live on Hidden Valley Road up in the Santa Cruz Mountains in Soquel, if you're familiar with it. And this is sunset and the dome. I had a refractor, and in here I had a nice, whoops, let me go to the next slide. I had a 16-inch RCOS, and on top there is a I think that's a Takahashi or some refractor I had. And there's a good old SIG CCD camera that I used to image with, and some of the pictures on the wall there that I took. But the problem that I had at my home is that we're at about 750 feet elevation up in the Santa Cruz Mountains, which means we still get fog. And so in less than a year, I noticed that the mirror, the finish on the mirror, the silvering on the mirror, the reflective surface was getting badly corroded, because before I could even detect the fog, the air was carrying salt, and the fog was very corrosive on the mirror. And so I had to pull the mirror. It cost like $2,000 to crate it and ship it and have it resilvered and put it back in. And so finally, I just had to close the observatory here because my location just was not a good home for a nice telescope like this. And back in those days, I was using film. This is Comet Hale-Bopp. I would sometimes travel to take a picture, and I used a Schmidt camera that Celestron used to make. Now they have the Rasa. It's all done digitally, but that was in the film days. And now I would shoot stuff like this. This is the horse head, of course. And that was a narrow band with a hydrogen alpha filter, not very high resolution. But, I was doing all kinds of astrophotography and wanting to up my game. And so finally, I moved, I had this set up, and I moved to a facility up in New Mexico called New Mexico Skies, up in Cloudcroft, New Mexico, it was close to 8,000 feet. Not a bad location. And I had two setups there. This is a Takahashi FSQ, and this is a camera, and then I had a lens on it. And here is a guide scope. And one of the things I designed and came up with, because back in those days, there was no way to focus a camera lens remotely. So this is in New Mexico. I'm in California. And so I used a servo motor, and I got a rubber belt, and I put it around the focus area. And using the servo from my computer in California, I could actually adjust and focus the camera lens. So it worked out quite well. Nowadays, of course, we don't need this old technology, but this is like the 1990s, early 2000 tech. If you wanted to photograph with a camera lens and do it remotely, then I had an old IBM PC, and using the one thing that always worked on a PC, it seemed, was remote desktop. So I had remote desktop in my home in California, and another PC there. I'd connect a remote desktop, which is connected to all the stuff, and I could operate the telescope. So with the FSQ,
Steve, quick question. You said with the camera lens, that's not the way that you would do it today. How would you do it today?
Remotely focus a camera lens.
Yeah.
I don't know. I haven't thought about that in a very long time.
Yeah. I think you have to do it exactly the same way, Steve. That's my point.
Yeah. Well,
I think you were right on the money with that.
Oh, good. Some of you may have done it here who have done astrophotography, but I'm sure they have much more sophisticated devices, because this was, I just used a rubber timing belt.
Yeah. But I mean, maybe there's something more sophisticated than a rubber timing belt, but I don't know of a technology that works for a camera lens. I mean, obviously for telescopes, you have all these, EAFs and, things like that. But when you're using a camera lens on a, let's say, DSLR or something, you don't have any way of auto-focusing that other than something like this.
Actually, I remember I saw something now. There's a thing you put on the camera.
We've had a few talks on this topic, and
there's a gear system. Yeah, go ahead.
All I wanted to say is we've had a few talks on this topic, and yes, you do it the same way. The advantage of today is, people have 3D printers. to print the various parts that make this a little easier to pull off, but it's fundamentally the same thing.
Well, and it was fun MacGyvering because you see the same focus motor here. This was the focus motor used for the FSQ that you attached. And so I just jimmied one, made a connecting stand and the proper gear and the rubber timing belt there.
Okay, thanks for the aside.
Sure, yeah. So, well, let me go back real quick to this. So one night I decided with the FSQ, and I also had in another building my 16-inch that I moved up to New Mexico. So we're up in New Mexico skies now. One night with the FSQ, I decided to photograph M81 and 82, which, very well-known galaxies. And I did a couple hours of exposure. Actually, it was more than that. I exposed all night, so it was probably 5-6 hours of exposure, and processed the image the next day. And while I was processing it, and I had it in Photoshop, I took the curves and I slid the curves all the way to the end just to see what I could see. I was just messing around, just brighten up the image. And what I saw in the image that night was this blotchiness all over the photo. And I was kind of shocked at what it was. And I thought, my God, it looks like there's smudges or grease on the lens somewhere. So, but I wasn't sure. So I sent the picture to a friend of mine at UC Santa Cruz, who's an astronomer. And I said, Mike, what do you think this is? And he said, I don't know, but we're going to find out if it's something on your lenses or something in the sky. If it's clear tomorrow night, just move your telescope like half a degree. And if you see the same pattern, you'll know it's in the telescope. If it's a different pattern, it's something in the sky. So the next night, which was Christmas night, I moved the telescope and I photographed and downloaded the images, stacked them up. And I'll never forget that. I got goosebumps because now there was new stuff. I could see the old part, but this was definitely in the sky. And it was around two galaxies that I had seen 1,000 photographs of. They were very common galaxies to photograph, but I'd never seen anything around it. So yeah, Mike's a good enough friend. I called him Christmas night and I said, you got to see what go look at your email. I said, what is that? And he said, wow, it's different. It's something in the sky. I have no idea. I'm going to send it to a guy, an astronomer in Great Britain. Maybe it's a new supernova remnant that you've discovered. And so that guy looked at it, and the day later, he emailed back and said, it is not a supernova remnant, but I've sent your photo on to an astronomy professor named Ron Reynolds at University of Wisconsin, Madison. And he studies, stuff in the sky, dust and clouds and all this. And so he sent it to him. A couple of days later, I got an email from Ron Reynolds, and he said, I think I know what this is. There's been a couple papers on it, and I'm going to send you one of the papers. It's a short paper. And he said the paper was written by an astronomer named Alan Sandage. And he said, look up Alan Sandage. Alan Sandage is still researching. He's in his 90s. He's at Caltech in Pasadena. And he said, Alan Sandage was really Edwin Hubble's only graduate student he ever had. So he sent me this paper, and it turned out that what I had stumbled across, but most astronomers, professional astronomers, had forgotten about it. Like the two who looked at it, they didn't know what it was. Amateur astronomers had never heard of it. And this is not M81 and M82. This is NGC 7769 and 7071. But all this other stuff that you see here, this is what they used to call high galactic latitude cirrus. So we have like cirrus clouds before a storm, very high, 60,000 foot up, thin clouds. And high galactic latitude means that this is not in the body of our galaxy. It's at the very outer edge. It's like an eggshell surrounding the galaxy. And the question is, what is it? And why can we see it? Why is it glowing? So I started photographing this stuff, and the astronomers that saw it were kind of astounded because they had never seen photos of this like I was taking. And I started doing a little catalog, which didn't get very far because the stuff was all over the place. And it's very blotchy, as you can see in the photo here. And so people started taking longer exposures and picking this stuff up. So then I got contacted by an astronomer in Ohio who said, I know what this is, and there's just me and 2 other people in the world who study this. It is this high galactic latitude cirrus. And I said, well, what is it? He said, what you're looking at is a complicated organic molecule called polycyclic aromatic hydrocarbons. And this is a mysterious kind of dust cloud that surrounds our galaxy. It's on the very outer edges of the galaxy. We're not sure where it comes from, but we do know that it is an organic molecule, which means that every molecule of it contains at least 1 atom of carbon. And so this astronomer, whose name was Adolf Witt, said, would you join our team? And we'll get a grant from the National Science Foundation. So we ended up getting a $50,000 grant. And with that grant, we built special filters so we could photograph this and study it. And so it was like my dream come true as an amateur astronomer. I got to work with professional astronomers, and we started mapping this stuff and analyzing it. And Adolf did papers, and I would take photos for the papers that were published in the APJ, which is the Astrophysical Journal. And so I got to be a co-author on professional papers in the APJ, as it's called. And then Sky and Telescope in July 2006 asked me to write an article about it. So if you pull up an old issue of Sky and Telescope, and they have them online, I think July 2006, I have an article in it. And I gave it a name because high galactic latitude cirrus didn't seem to do it justice. And I talked this over with Dr. Witt, and I named it Integrated Flux Nebula. Now, when you think about nebula that we like to photograph, like the Orion Nebula or, all the stuff in the Milky Way, we have these clouds of mostly hydrogen, and those things are glowing quite brightly because they're excited by hot, bright stars that are nearby. And, the gas, the electrons are getting knocked out of orbit, and it's emitting light in hydrogen alpha, from the hydrogen, and we're able to pick it up with our telescope. But the gas that you see here is not near any stars. And once again, you see the bright stars here, but this gas is way beyond those. It's not near any stars. So the question became, what is making that gas glow? And it turned out what's making it glow is the integrated energy of all the stars in the Milky Way galaxy. So imagine all this energy coming up from the galaxy. It hits these molecules, knocks electrons out of orbit, and then when the electron jumps back, this is quantum theory, of course, it emits light. That's the essence of fluorescence. That's how fluorescent lights work. They get electricity knocking electrons out, and depending on what gas you have in a fluorescent tube, you get blue or pink or red or yellow. And it's a little hard to see, but you can see some of it. I don't know if on your monitor you can see here a little red in it, and there's some red there, and a little red in here. And the integrated energy or flux of all the stars in the galaxy is causing these dust particles essentially to fluoresce in the red, and it's called extended red emission, ERE. There's also, in some of this, but not much, it's not as common, it's called blue fluorescence, and some of the clouds I photographed are putting out energy, they're putting out red and blue simultaneously. And it's not because they're reflection, it's not because there's a particular hot star, it's the integrated energy of all the billions of stars, the hundreds of billions of stars in the Milky Way galaxy that causes this stuff on the outside to glow. So it looks like this is buried in the dust, but it's not. The dust, all this stuff is way in the background. And that's what this faint stuff is. So I've been given credit, which is incorrect, that I discovered this. I did not discover it. I kind of refound it. They knew something was out there, but I figured out how to photograph it and participated in a lot of the studies. And once amateurs saw this, now you can look up a lot of photos that amateurs have shot. And with the excellent cameras and telescopes we now have, people capture the IFN, Integrated Flux Nebula, very frequently. And so with our telescope here in the Sierra Nevadas, I photographed these two galaxies, and they're in Pegasus, because I know in Pegasus, there's way in the distance, there's a large clouds, and then the galaxies, of course, are behind the clouds. So it's really, once again, you have to think 3D with this. So this really got my juices going, because I was able to work with professional astronomers, and it was so much fun. And from that, and I was in my 50s, I'm 75 now. I was in my 50s when all this happened, and Dr. Witt offered me entry into the PhD program in astronomy and astrophysics. But to do that, I would have had to move my family, and I had two boys in high school, to Ohio, and that wasn't going to. So I said, thank you so much. I'm very honored that you would want me to do that. But, you know, I've got my consulting company and a family. So, but I was very flattered that I got the joy of discovery, the joy of finding this and educating people as to what it was. And you don't need a hydrogen alpha filter. If you try to use a hydrogen alpha filter, which we would normally use to photograph like the Orion Nebula, this doesn't even show up with a hydrogen alpha filter. This is just with a standard LRGB filter. It's a broadband emission, it's not a narrow emission, and you can pick this up. So anyway, this got me even more interested in astronomy, and made me think, boy, I wish back in the day I had stuck with the sciences in college. So, any questions about this? Yes. No. Hi. Did you have a question, or you're just saying move on? Okay.
No questions. Gotcha. Thank you.
Okay. So, so what I have now, this is my backyard. We're up in the hills here. I have a little solar observatory. So I got a couple of solar scopes. Those are Lunt scopes. This is the 100 and the 152. I'm actually selling this one. So if anyone wants a high-end Lunt solar telescope, this one's for sale. And, with those scopes, I can get, stuff like this, photos of the sun, which is kind of fun to do. I haven't done a lot of solar photography, but it's quite dramatic to see stuff like this. And then I decided, along with my buddy Bob Farah, to put telescopes up at Sierra Remote Observatory, SRO. And so here's two of the guys putting in the mount for our telescope. We have plane wave 17-inch scopes. This is the plane wave 500 mount that they're putting in. And there's Bob with our 17-inch we're about to put up there. And there it is, put together. And now we've got our camera and Eagle computer up there. And you've heard of junkyard dogs. Whoops. There is the observatory dog. So that's Sam, one of the technicians there. That's his dog who gets the run of the building, and really friendly pooch guarding our telescope. All right, so here's the telescope at night, and this is just a little video. So we call them spy cam. We can put a little security camera away from the telescope, and we can actually tune in and watch the telescope moving. And these cameras are so good, they pick up the night sky here. And here we're doing a modeling run. So we have a pointing model, and we tell the telescope, find 100 stars and map them out so that the pointing gets very, very accurate. And so we could keep watching this, and the telescope is slewing, is taking a picture with the camera here. The computer then reads the position, how accurate is it? And if you shoot about 100 stars, it makes your pointing very accurate, and it tells you your polar alignment error. And so then, we do a mapping run, and then I'd call the guys the next day and say, okay, raise the altitude 1 degree, move the telescope east, this far. And we do tweaks over a couple nights until we had really excellent polar alignment and really excellent pointing. And there you see a little satellite going by. There it goes. And the telescope is doing the mapping run. Here's our telescope in Chile, and it's another 17-inch plane wave. And I put this shot in. So this is in Chile, and it was a full moon. So no one was really taking pictures, but what they did is for some reason, they opened the roof, and it was a full moon. So this isn't the daytime shot. You could see all the stars in the sky. This is a full moon shot. And I thought this was really cool. You see all the domes, and they've got other buildings here. And what you see in the back are the snow-capped Andes. So I took a screenshot of this because I just love this image of the building with the Andes and the stars under the full moon. Okay, so about 10 years ago, before I had a telescope there, I went with a friend of mine, a guy named Matt Scott. Matt was president of the Carnegie Institute for Science in Washington, D.C. And I've known Matt for many, many years. And Carnegie runs the Las Campanas Observatory in Chile. And he said, hey, I'm going to Chile. Do you want to go? So I said, yeah. He said, we're going to go visit the big observatory. We get to stay in the dormitory there. Actually, everyone has their own little room. It's quite nice. So I went with him to Chile, and I met a couple of astronomers and started talking about the Magellanic Clouds. And the Magellanic Clouds, of course, are the two little satellite galaxies, the Milky Way, that are pretty close, and they're small, and they're being sucked into the Milky Way. So I was very interested in photographing them, but they're quite near the South Celestial Pole. And the telescope in Chile, even though it's in the southern hemisphere, that the Magellanic Clouds are not high enough, long enough. And I wanted to do some studies of material that's flowing from the clouds into the Milky Way galaxy. So with this guy, Steve Boddy, who, if you remember, he's one of the people from the Deep Sky Collective, one of the three guys, the guy in Melbourne, Australia. I said, hey, I want to put a telescope system in southern Australia, get as far south as possible. Do you know a facility? He said, yeah, there's a small facility. It's about an 8-hour drive, but I'll partner with you on it. And so we put a FSQ there. And up here, we have a 135 millimeter camera lens. And it's focused because we have it on a rotator. So this will move the camera in and out. So you asked me earlier about focus. You could do it by turning the band on the camera lens, but you could also move the camera. So this one moves the camera. And we have the 135 millimeter lens, so we can do some very wide surveys of the sky. And then when we find things that we want to photograph, we'll use the larger telescope here, the FSQ, to photograph those objects. So this just got set up. I'm going to show you our first picture taken with this in a little bit. Here's our spy camera, so we can actually watch this telescope and see the night sky in the background as it's operating. And this is all set up and working extremely well. So we call our little enterprise DSRO, which is the Deep Space Remote Observatories. And we have the 3 telescopes now, and we're about to add a 4th telescope, which I think is going to be set up at a facility in the Southwest. And it's going to be one of these again, at FSQ, mainly designed to do pretty wide field studies. But we've put a reducer lens on these because the native focal length is f5, but we want it to be faster because we're photographing some very faint stuff. And so we reduced it to f3.6. So we have 2 very fast systems that will be shooting them. Okay, well, here's some of the objects that we have photographed, in the last year. And I thought I'd show you a few of these. And I'll just kind of walk through these. They're just pretty pictures. Whoops, going the wrong way here. And these are very interesting. DEM are the initials of 3 astronomers who discovered these 2 objects that are just located in one of the Magellanic Clouds. Randomly, this galaxy is here, and I don't even know the designation of this galaxy, but it's quite far in the distance. So these objects in the Magellanic Clouds are about 160,000 light years from the Milky Way galaxy. And that galaxy out there, I'm just guessing, is probably in the 20 to 40 million light year range, much further out. So once again, think in 3D here. And we photographed these 2 objects. There's still a lot of speculation about what they are. No one's quite sure, but everyone's leaning towards a supernova remnant because it's photographed with hydrogen alpha and with oxygen 3, so O3 as it's called. And those are both signatures of supernova remnant. Here's the well-known Helix Nebula. And when we photograph now, we're using a lot of narrowband filters, and we do long exposure. So most of our objects, we spend somewhere between 20 to 40 hours of exposure time. And because we're in dark site locations, we're getting excellent resolution, and we have good equipment. You can see, the resolution on this is quite wonderful. And so this is the kind of stuff we're able to get. Here's an IC object. This is another planetary nebula, Jones 1, mostly oxygen 3. Very interesting shape, obviously. Oops. And Galaxy 1291. I'm just going to run through some of the pictures here. So you can see we're getting pretty good results with our telescope. I just thought this one was really interesting. This little guy is kind of interacting, and then this arm has just been pulled off. A lot of gravitational interaction going on there. This looks like NGC 4565, but it's 7814, another edge-on galaxy. And this is the Vela supernova remnant. And this is the first picture we took with the new telescope in Australia. So very wide field. And you could see we got a huge amount of detail in this image. And this was, how many hours? This was a mosaic we did. So probably close to 100 hours, but that's because there were 6 panels we were shooting. And we didn't even capture the whole nebula. So we're now shooting on the outer edges. We're shooting out in this area and more out here. So we're going to expand this. And because it's a mosaic, we have so many images, we'll be able to make a giant wall print. I mean, this could be, the resolution is so good with the system And with the number of photos we're taking, we calculate we could easily make a 12-foot long by 6-foot high print of this if we wanted to. Another NGC object. Same thing. And you know, we love interesting planetaries. This is quite an interesting structure in this thing. HFG, once again, initials of astronomers who were involved in the study of this and identified the object. M78. And just, here's this is known as the Pencil Nebula. And in the past with film, this was the bright part right here. And look, people said, oh, it looks like a pencil, where they weren't picking up all this other stuff. So now it's like people look at it and go, I don't see a pencil. But a lot of the older photos didn't pick up the detail that we're able to pick up. You can see, you know, the resolution is astounding. So this was taken from Chile, and this is part of the Bella supernova remnant. It's one little piece of it that we shot with a 17-inch scope to pick up the detail. And the Tarantula Nebula in the southern hemisphere, which is just fantastic. I mean, you just get lost looking at the little pieces here. So that's kind of the end of my presentation. If any of you have further questions, take a screenshot, if you would, of this. So here's links for you, my contact information. We have a site for DSRO on AstroBin. So if you've never been on AstroBin, I suggest you look at it. AstroBin now holds over 1 million photos, amateur photos, and some of them are really quite amazing. In the ADF project, which Hai sent out a link to that already. And then the Hubble Deep Field lecture that I recommend, so you can see Bob Williams talk about this and tell his story, is that last link there. There's the end. There's my last slide.
Thank you very much.
Thanks for listening. Yeah. So if there's any other questions or comments, happy to hear them.
Yeah, anybody have some more questions for Steve?
What computer program do you use to control your equipment?
So right now, for the telescope in the Sierra Nevadas and the one in Chile, we're using Voyager. For the telescope that is in Australia, we're using Nina. And the one we're going to put up in the Southwest will also use Nina. And we may switch over to Nina instead of Voyager. Like Voyager has worked pretty well for us, but we want some additional capabilities that we really like that Nina has. And also we have to pay for Voyager every year, and Nina is free. And Nina has really developed, you know, 5 years ago, it was nowhere near as good as it is now. So it's quite excellent.
Are you located in Santa Cruz yourself?
Yeah, so I live in SoCal.
Okay. All right. I'll be down there tomorrow getting plants, vegetables to grow.
Oh, where do you get them?
At Love Apple Farm.
Oh, all right. Yeah, so it's the weather's been cold over here, but we got the coastal fog.
It is, but it's just on the verge of changing. So it's time that I buy the little 3-inch plants and then replant them with planting soil in pots and let them grow up to be a foot or two high before I put them in the ground.
There you go. Good time to do that.
All right, I'll contact you. I need some help with Nina.
Oh, first of all, I got to tell you, I operate Voyager, and our guy in Australia operates Nina. I couldn't tell you anything about Nina.
Okay. Thank you.
I wish I could. I want to learn the program, but since we just put that telescope in, and Steve, the other Steve in Australia, knows it. He's been doing the programming in Nina, but Bob and I have not learned it yet.
Thank you.
Wish I could help you with that.
Hey, Steve, I have an astrophysics question for you. So in your deep field images, the really distant galaxies that you pointed out were little blue dots, right? Which is interesting because, they were like they had a Z of 1 or 1.5. So that means that they were even bluer, right? Like that they were ultraviolet or whatever.
Yeah,
Which is
they were
interesting.
rich. Yeah,
Yes, so they're
uh,
they're very redshifted and they're blue in your pictures. So does
correct.
that mean that they were incredibly? Oh, those are quasars, says Nick. Okay, there you have it. So the blue comes from the gigantic black hole in the middle. Okay,
That's
thanks, Nick.
that's part of it. That's part of it. And so, when things get redshifted, they're so redshifted, especially the distant ones, that it goes into the NIR, the near infrared and the infrared, right? But our camera sensors are only picking up stuff on the other side. And so since the energy has been brought down, we're picking up some blue there, and there's a couple other explanations because I had the same question: why don't these things look red? And so someone explained it, and I can't re-explain it to you because I got to go back. An astronomer wrote me an explanation, but I can't regurgitate it for it to make sense.
All right. Well, like I say, Nick says they're quasars.
They
So
are, they
that's
are.
another one for you. So we're
They're
actually seeing not the galaxy so much as the really bright thing in the middle of the galaxy.
they're they're at that point when we can see them, they're called AGNs or active galactic nuclei, which is he's correct, it's a massive black hole that's throwing out the light.
All right. Are there any other questions for Steve before we let him go?
Yeah, one quick question, Steve. All these telescopes that you're putting up, obviously they must cost a lot of money. Are you getting funded from somewhere, or is it all self-funded?
Um, no, I should be robbing banks, but I'm not to put these telescopes up.
Yeah, I
So
was wondering if it's coming from UC Santa Cruz or something else or whatever.
no, I get no funding. Bob and I
Okay,
have both retired, and instead of buying
self-funding.
fancy,
Okay,
yeah, we bought telescopes.
got it. Very nice, very nice.
Well, thank you. And thanks for tuning in tonight. And I hope this was interesting. And I'm happy to, like I say, answer questions or help if you're just getting started in astrophotography. I love this stuff, obviously. So don't be shy if you want to reach out.
Thank you.
All right. I guess we're at the end. So everybody, please unmute and give Steve a big round of applause. Thank you so much, Steve, for that wonderful presentation.
Thank you. My pleasure.
Yeah, thank you.
Nicely done, Steve.
Way to go, Steve. It was awesome.
Yeah,
Thank
Okay,
you.
thank
awesome.
you.
All right. Thanks very much. And see everyone next month, hopefully.